7, which is the steady state errors. This is the chapter 7. Okay, so in this chapter we'll say a few things like what is a steady state error, and some regarding problems. Okay, so what is the definition? See, steady state error is the difference between the input and the output for a prescribed test input as t tends to infinity. Test inputs used for steady state error analysis and design are summarized in table 7.1. See, so what is the steady state error? This is the difference between the input and the output. The error, that means the error. Error is the difference between the input and the output. See, that is the step input. In the step input, physical interpretation, constant position, time function 1, Laplace transform 1 by s. Ramp, constant velocity, time function t, Laplace transform 1 by s square. Parabola, constant acceleration, half t square and 1 by s cube. See, so remember this table. Test waveforms are evaluating steady state errors for of position control system. Okay, so steady state error is the difference between the input and the output for a prescribed test input as t tends to infinity. Test inputs used for steady state error analysis and design are summarized. Okay. Now, let's go to the, what are the sources? Many steady state errors in control system arise from nonlinear sources, such as backlash in gears or a motor that will not move unless the input voltage exceeds a threshold. Nonlinear behavior as a source of steady state errors, although the viable topic for study is beyond the scope of it. Okay. Okay, now steady state error for unity feedback system. So if we have the unity feedback system, then what would be the steady state error? Okay, so we have to check this one. See, steady state error can be calculated from a system's closed loop transfer function, which is the TS, or the open loop transfer function, which is the GS. For a unity feedback system, we begin by deriving the system's steady state error in terms of the closed loop transfer function, TS. In order to introduce the subject and definitions, next we obtain, okay, after that they will discuss about the GS, system with the GS, that means the open loop transfer function. Now see, steady state error in terms of TS. So from the definition, we know that this is the difference between the output and input. So if the input is the RS, so to find ES, the error between the input RS and the output, so RS minus CS. Okay, but we know CS is equal to RS into TS. So put this value here, then you will get the ES is equal to RS into 1 minus TS. Now, although equation 7.4 allows, okay, ET at time t, but we can write like this. So if we consider the time limit, t tends to infinity. This is called the final value theorem, which allows us to use the final value of ET without taking the inverse Laplace transform of ES. Okay, so we can write like this. So if we consider the S, and then ET, what is the ET? It is the SES. Okay, so after that, just put the value of ES, then So you know that ES is this one, this one. Okay, that is the equation or the closure transfer function to find out the error. That is the final value theorem. Okay. So the final value theorem is derived from the Laplace transform of the derivative. So that is the final value theorem. Okay, let's look at the example. Find the steady state error for the system of figure 7.3a of TS. Okay, so let me look at the figure. Uh, Figure 7.3. Where at the figure? This one. Okay. This is the figure. Now check this one. Uh, Find the steady state error system 7.3a if TS and the input is the unit step. So what they did from the problem statement RS 1 by S, TS is equal to 5 by this one. And if we substitute it into the equation 7.4, so what is the equation 7.4? Let's see, RS into 1 minus TS. So if you put this one, so ES is equal to RS into 1 minus TS. So we have the value of RS, which is the 1 over S, and if we put the value 1 minus TS, that means that TS S square plus 7S plus 10, 1. So S square plus 7S plus 10 minus 5. Then after that the equation will look like this: S square plus 7S plus 5 by S into S square plus 7S plus 10. Okay. Since TS is stable and subsequently since TS is stable and subsequently S does not have right half plane or poles or j omega poles other than that, we can apply the final value theorem substituting equation 7.7 to equation 7.5 gives just this one. Put this one into 7.5. So which one is the 7.5? So this one. Limit S tends to ES. So if you put this value, okay, if you put this one, say limit S tends to infinity is yes. Now put this one, then SS would be cancelled out, so ES will be there. So if you put the value of 0 here, value of 0, so it would be 0, it would be 0, it would be 0, it would be 0. So 5 by 10, so it would be half. Okay, so it would be half. So like this you can find out the value of error. So if it is stable or not, you have to determine the root table, okay, for this one. So let me check the root table for this one. S square, that means S square is 1 is 0. Okay, so 1, 10, 7, 0. After that, what is the value? It would be 7, minus 10 0 0 0. At the same minus 57, that would be 0 0. So here the value is 0, all are things 0. So no sign change. So since there is no sign change in the first column, so it is a stable system. It is a stable. So if it is a stable, then yes, does not have right half plane poles or j omega poles other than that at the origin. Okay, like this. So this is the 7.1. Now if we move to the GS, in terms of GS, okay, many times we have the system configured as a unity feedback system with a forward transfer function GS. Although we can find the closed loop transfer function TS and then proceed as in the previous subsequent, we find more insight for analysis and design by expressing the steady state error in terms of GS rather than TS. Now, consider the feedback control system in number 3b. Since the feedback HS equal to 1, the system has the unity feedback. The implication is that ES is actually the error between the input RS and the output CS. Thus, if we solve for ES, we'll have an expression for the error. So we'll then apply the final value theorem. Okay. So we know that RS minus CS, but CS equal to ES into GS. So put this value here. Yes, finally substitute equation 7.9 to 7.8. Now put this value here instead of CS, ES into GS. ES into GS. So do the calculation. So it would be RS into 1 by RS by 1 plus GS. Now the equation would be like this. Okay, the error equation. Okay, so we'll use this equation. So if you have the step input, then it would be look like this. Okay, so if you have the ramp function, then it would be look like this. Okay, final equation would be look like this: 1 by limit s tends to 0 s into gs. And if you have the parabolic input, 1 by limit s tends to 0 s square into gs. Okay, so these are the thing. Now check this one. Find the steady state errors for input 5 UT, 5 TUT, 5 T square UT to the system shown in the figure. Okay. So now let's look at the 7.5. This is the 7.5. So for this system, you have to find out the steady state errors for the inputs. 3 types of inputs. So first one is the step, then ramp, therefore parabolic. Okay. So 3 types of inputs are there. So for them you have to find out the steady state errors. Okay, for this kind of systems. Okay, so feedback control system for the see. First, we verify that the closed loop system is indeed stable. For this example, we leave out the details. Next, for the input, so you have to check it is stable or not. Okay, so you have to check it first. Is it stable or not? Okay. So for this one, so at first of all, you have to check this out. So this is the step input, equation for the step input. Okay, so we'll check. So it is the 5 by 21. Okay, then ramp input 5 by 0. Then the parabola 10 by 0. Okay, now let's look at the equations here. All are one. So first of all, you have to consider this one. You have to, let me show this one step by step. So this one. Okay, so what is this? In s square plus s square plus 4s. Here the 3s, that means 7s plus 7s plus 12. Okay, in the lower part. The upper part 120 into s plus 2. 120 into s plus 2. That is the lower part. And here what you can do after, and if it is stable or not, just use this equation. Okay, use this equation here, put this one here. So for the input 5 ut, see 5 ut, that means 5 by s. So 5 by, so here put this value. If s is equal to 0, then what would happen? It would be 120 into 2. So if s is 0, that is the 12. So 12, 10. So it would be 20. So 20 plus 1, 21. So again 5 by s square, 5 by s square. So for the input 5t ut, whose Laplace transform is 5 by s square, this error will be 5 times that given equation system. So this is the equation 5 times larger. The put this value here again, then it would be infinity. Like this way. Okay, like this way, you have to check this one.
Third question.
Yes, please.
Sir, how we can determine that the system is stable or not?
Okay, in that case, you have to check the root table. Root table here. So what was the equation was 120 s plus 2. In the lower part, it was s square plus 7s plus 12, right? Plus 12. So you check this one, s square is 1 is 0. So 1, 12 and 7, 0. Here the equation 12, 0, 0, 0. 12, 0, 0, 0 by 7. So here all whole things would be 0, right? Whole things would be 0. So there would be no sign changes. No sign changes. So it is a system, is stable. So just you do not need to solve all, just check the rough thing, do the rough. Okay, if it is sign change, then the system is unstable. If there is no sign change, system is stable. Okay, you have to check this one. Okay, so they leave out for the details. That is the thing. They have not do the full thing. Have not done the full thing. Okay. So next thing, see here. We have seen that only a step function is finite, but those are infinite. Okay, this output for this input, ramp and parabolic input, you have found the output is infinity. Okay, that means the error is infinity, infinite error. They have given another example here. Find the steady-state errors for the inputs 5UT, 5UT, and 5TSKT for the system showing figure number 6. So this is another one. Okay, first verify the closed loop system. First verify the closed loop system. Okay, in the indeed stable. So if it is a stable, next note that since there is an integration in forward path, the steady-state errors for some of the input waveforms should be less than. Okay, so you have to first check this one if it is stable or not, like the root table. Okay, check the root table. Then step function. Here put the value of GS, ramp function, and the parabola. See, in the RAM, it is the finite value. For the input 5t ut whose Laplace transform is 5 by s square, the steady-state error will be 5 times as large as that given subsystem. So it is the finite value. Okay, notice that the integration of the it is the difference. Okay, so first of all, you have to check this one using the root table, then you do proceed. Okay. And this is a unity feedback system has the following forward transfer function. So that is the forward transfer function. Okay, so you first of all you have to check it is stable. If it is stable, then you can move. Okay, now just put the values here and check. So the closed system is stable for 15 ut step function 0, 15 ut is 2.1875, 15 t square ut is infinity. This is unstable. How it is unstable? Let me check. So let me check this one. First of all, you have to calculate this. So this is the s square, s plus 25, s plus 35, s plus 50. So just do the calculation. Okay. Uh, this is the first one by one. So s cube plus 25 s square, 25 s square into s square plus 35 into s plus 50. Okay, sorry, this is not the s square. Let me clear this one. S plus 35. Okay, now see s cube. Calculate this one with this one. So s to the power 4, s to the power 4 plus 35 s to the power 4, 35 s to the power 4, sorry, 35 s cube, 35 s cube plus see 25 s square, 25 s square, so it would be 25 s cube, 25 s cube, 25 s cube plus 35 into 25. What is the value? 35 into 25. 30, 35 into 25. Someone calling me on the messenger is very irritating. So what is the value? 35 into 25, 875, right? That is 875. Okay, so it is 875, and here is plus 50. Okay, then again do the calculation here. S to the power 4 plus 35 plus 25, that means 60 s cube plus 875 into s plus 50. Now again check this one. Let me erase this one. Okay, do the calculation. S to the power 5 plus 50 s4 plus 60 s to the power 4 plus 300 s cube plus 875 into 50. 875 into 50. 875 into 50 means the 43750. Okay, like this. Okay, then you do the root table. S4, S3 up to this. Then you check this one. Okay. Then you will find that it is not stable. Okay. Now static error constant and system time.
Sir, S plus 50. Where's from?
Here.
Where's from, sir?
S plus 50, just you do the calculation here. Okay. Just you have to calculate it this. I just did the rough. Okay. Just multiply this one. If you multiply this one, then you will see what is the equation. Then put it in the root table. Okay.
Okay, sir.
Okay. It comes from here. Now the static error constant. See, so that is the equation we have found here. Okay, for three types of inputs: step, ramp, and parabolic. Okay. Now this one terms as the position constant, or Kp. This is Kv, velocity constant, that is Ka. So three kind of constant we have considered here. Okay. So three kind of constant. So that is the Kp, position constant. That is the velocity constant Kv. That is the acceleration constant Ka. Okay, remember this one: position constant, velocity constant, and acceleration constant. Now for each system of figure 7.7, evaluate the static error constants and find the expected error for the step, ramp, and parabolic inputs. So first of all, you have to check this one. So three figures are given. First, verify that all closed loop systems shown in is stable. So if it is stable or not, use the root table. Okay, just do the rough root table. If those are stable, then check the constant kp kvk. Okay, kp kvk, find out, then put this for the step input, for the ramp input, for the parabolic input. So see, for the step input, this is 0.161. That is for the first one, and the second one, for the second one, like this same way. Okay, so they have done for the all three. So they have found the output. Okay, so generally in the exam I give this kind of problem. Okay, so you have to find out the kp, kv and ka, then put this for the equation, error equation, steady state error, find out the error. Now say system type. So a step input steady state error formula 1 plus 1 by 1 plus kp. Kp is the constant, error 1 by 1 plus kp. So this is a type 0. If kp is constant, other two are 0. Type 1 error, kv is the constant. Type 2 error, k is the constant. So from a math we have to find out which type of error it is. So first of all, given a unity feedback system. So for the evaluate system type kp, kv and ka. So find out the kp, kv and k and determine the system type. So kp is 127, kv 0, ka is 0. So it is the type 0. Type 0. And see, find the steady state error for the relationship. Step, ramp and parabolic input. See, simple one. So check this one also, 7.2. And here, say what information, okay. And another problem is given here. Limit. Given the control system in figure 7.10, find the value of k so that there is 10% error in the steady state. So 10% error. Since the system is type 1, so which type of system you have to first calculate. The error stated in uh, the problem must apply to a ramp input. Only ramp yields a finite error in a type 1 system. So infinity 1 by kv 0.1. So therefore kv is, put this value, this one. So which is k is equal to 672. Okay. Disturbances. Okay, so see here, non-unity feedback system. What would happen if you have the non-unity feedback system like this? For the non-unity feedback system, let's look at the example. This is not the non-unity feedback system. It's registered error for non-unity feedback system. For the system shown in figure, find a system type, the appropriate error constant associated with this system type, and the suggested error for a unit step input. Assume input and output units are the same. So GS and HS, we know the GS and HS. So find the equivalent GE. So it is the equivalent. Now put this one KP, KV. If it has some value, so other two will be 0. The other system is type 0. Okay. The appropriate static error constant is then KP, whose value is this one. So the steady state error, this one. So negative value for steady state error implies that the output step is larger than the input step. So output is larger than the input. That is the negative meaning. So check this problem also, which is a 7.8 problem, 7.8 also. Okay. And they have given another example. Find the steady state error actuating signal for the system 7.16. Which one is 7.16? This one. For a unit step input, repeat for a unit ramp input. Okay, same thing. Now sensitivity, it is the last part of this chapter. Sensitivity, what is the sensitivity? See, during the design process, the engineer may want to consider the extent to which changes in system parameters affect the behavior of a system. That means the how much, okay, the threshold level. Ideally, parameter changes due to heat or other causes should not appreciably affect a system's performance. The degree to which changes in the system parameters affect system transfer functions and hence performance is called the sensitivity. The degree to which changes in system parameters affect system transfer function and hence performance is called the sensitivity. Okay, the degree, that means that the degree to which the changes in system parameters affect system transfer function and hence performance is called the sensitivity. A system with zero sensitivity, that is the changes in the system parameters have no effect on the transfer function, is ideal. So if the sensitivity is zero, then it would be ideal. The greater the sensitivity, the less desirable the effect of a parameter change. Okay, so for example, assume the function f k by k plus a. If k is equal to 10 and a is equal to 0, then f equal to 0.091. Okay, so that is the function. So if parameter a triples to 300, then f becomes 0.032. We see that a fractional change in parameter, a 2% change yields a change in the function 65%. Okay, thus the function f has reduced sensitivity to changes in parameter a. As we proceed, we will see. Okay, so that is the equation. Limit del p tends to 0. Fractional change in the function f divided by fractional change in the parameter p. So finally, this is the equation. So they have used a problem. Given the system in figure 7.19, calculate the sensitivity of the closed loop transfer function to changes in the parameter a. How would you reduce the sensitivity? So at first of all, they check this one, k by s into s plus this. So find that ts, this one closed loop transfer function. Now put the value a by t, del t by del a by t, del t by del a, del t, this one. We know that ts, so that is a del t by del a. Calculate this one, minus s by s, which is in part a function of the value of s. For any other value of s, however, an increase in k reduces the sensitivity. Okay. So like this. So they have took the check the 7.10, 7.11, okay, 7.12. Different types of inputs are there, and they have shown it. Okay. So up to this, our target. Okay, let me check this one. Say sensitivity for the state with the step input. So k and a. Okay, so that is the equation though. So this is error for this type 0 system is, so find the error parameter a e sensitivity, put the value here, k by k. The sensitivity to change in parameter k is, okay, for a and k less than the unity. So see, K is less, A is higher. Since it is minus, so the last. Thus the feedback in this case, it's reduced sensitivity to variation in both parameters. So if you change the parameter, then the sensitivity will change. Okay. So let me show you. Okay, I'll show it later. So that is our part. Let me show you another thing, which is from the PowerPoint presentation. Same thing. Stability, steady state error. Let me show you. You see this steady state error, chapter 7. See, this is your courses. Sources of steady state error for unity feedback system, a static error, constants and system types listed for non-unity feedback system, and sensitivity. See, so I'll share this one with you. That is the same thing from the book. Okay. Specific things are there, so you can check this out. Okay, some maths which I have discussed, okay, are given there. Okay, sensitivity, problem solve button, up to this. So that is your sensitivity chapter. Okay, so I